Hello guys, and welcome back to Introduction to Number Theory. This time we will discuss a very famous theorem that belongs to a very famous mathematician. This mathematician is Fermat, Pierre Fermat, and the theorem is called Fermat's small theorem because we all know Fermat's great theorem. It was proved about 20 or 25 years ago. Well, Fermat's small theorem states that for every prime number p and every integer number a, in case if a is not divisible by p, then a to the power of p minus 1 is congruent to 1 modulo p. Well, this means that if we take a and raise it to the power p minus 1, we will gain an integer which will give remainder 1 when divided by p. What does this mean actually? Let's consider an example. For instance, if p is equal to 7, then take a equal to 1, raise it to the power 6, gain 1, and obviously this number is congruent to 1 modulo 7. Another integer 2 to the power 6 is equal to 64, which is precisely 63 plus 1, and 63 is obviously divisible by 7. So 2 to the power 6 has remainder 1 when divided by 7. What about 3? Well, 3 to the power 6 is equal to 728 plus 1, and it's easy to check that 728 is divisible by 7. So 3 to the power 6 also has remainder 1 when divided by 7. What about 4? Well, numbers get a bit larger now, but nonetheless, 4 to the power 6 is also equal to something divisible by 7 plus 1. So it has remainder 1 when divided by 7. The same we can say about 5. 5 to the power 6 is equal to 7 times 2232 plus 1, which means that it is also congruent to 1 modulo 7. And finally, 6 to the power of 6, we see that it is also something divisible by 7 plus 1, so is also congruent to 1 modulo 7. What about all the other integers? Well, we understand that all integers can be represented in the form something divisible by 7 plus remainder. And when raised to the power arbitrary power n, then we also have something divisible by 7 plus this remainder to the power n. So we checked all the remainders except for 0, because we know that in Fermat's small theorem, a should not be divisible by p. In our case, a should not be divisible by 7. And in all of these cases, for all these remainders, we saw that their sixth power is really congruent to 1 modulo 7. What about numbers that are maybe divisible by p or maybe not divisible by p? If we consider, once again, arbitrary prime number p and arbitrary integer a, and we don't know whether a is mutually prime with p or is divisible by p, can we say something in general about a to some power? Well, actually, yes. Fermat's small theorem can be generalized for all integers a, only in this case we need to take a to the power of p, and it will be congruent to a modulo p. In order to prove this, we will consider two cases. First case, if a is divisible by p. In this case, a to the power of p as well as a both are congruent to 0 modulo p, so they are congruent to each other also. The second case, if a is not divisible by p? Well, in this case, we can apply Fermat's small theorem and say that a to the power p minus 1 is congruent to 1, and then just multiply this congruence by a to gain that a to the power of p is congruent to a modulo p. So this really works for all integer a's, all integer numbers a and prime number p. Let us now consider an example. Say if we have 6 summands, all of them are 6 powers of integers, a, b, c, d, e, f, some integers, and we suddenly find out that their sum, the sum of these 6 powers of these integers, is divisible by 7. It is amazing that in this case we can really state that all these integers should be divisible by 7. Well, it's amazing if we're not used to Fermat's small theorem, but now we understand that a to the power 6, b to the power 6, c to the power 6, and so on, all these integers, all these 6 powers, are congruent to either 0 or 1 modulo 7. So, in order to have a sum that is congruent to 0, which would mean that it is divisible by 7, we need to have 6 zeros. So all these numbers must be divisible by 7.